Okay, so good afternoon, everyone, or good morning, depends upon where you are. I guess good afternoon for most of you. I am Steven Emerman. I'm in Spanish Fork, Utah. I'm the owner of Malach Consulting, and I'm going to be speaking about how flood-affected communities can work with flood scientists. Okay, so just a quick biography of me. I have a master's in geophysics from Princeton, PhD in geophysics from Cornell. I was a professor of hydrology for 31 years. Then I retired and started doing full-time consulting. I was a Fulbright professor in Nepal and Ecuador, and that's what I look like. Okay, so my business is Malach Consulting, and what we do is we provide technical assistance to communities concerned about potential and actual impacts of development projects. And my number one area has been impacts of mining projects, and we've worked with a lot of indigenous communities in this regard. Second has been logging, forestry, and recently I've been getting much more involved in impacts of urban development. I've worked quite a bit with 4 flood-affected communities: Houston, Texas, Richwood, Texas, Gulfport, Mississippi, and Charleston, South Carolina, which is also my birthplace. All of this work with flood-affected communities, as Harry had mentioned, has been connected with American Geophysical Union, Thriving Earth Exchange. I have quite a few more flood-affected communities coming up. I will be speaking with communities from Pensacola, Ellicott City, Maryland. I've already been communicating with Staten Island, so hopefully this list will be growing. Okay, so if you've interacted at all with the regulatory agencies, municipal departments, stormwater professionals, the concept of a model has come up. Okay, and this is what I really am devoting this entire time to, is talking about models, what they are, how they work, what goes wrong, why they so often go wrong. Okay, so what does this word mean? It tends to mean 2 different things depending upon the context, but they're connected. The first is that a model is simply a possible answer to a question. Doesn't have to be the correct answer, but any possible answer, we call that a model. Okay, or sometimes by the word model, we mean our framework for answering questions, or how we're going to go about answering questions. Okay, so I call this a possible, idealized, and simplified representation of reality that can be used to answer questions. Okay, doesn't mean it's correct, but it's a possible way to do so. Okay, so what might a model be that's used to answer questions about flooding or stormwater? It could be a combination of a topographic map, a land use map, a map and a description of the municipal stormwater infrastructure, a set of equations that describe stormwater flow. So that's going to be our representation of reality, and we can use that to answer questions. Okay, now, I want to explain what is so important about this idea of model and how we distinguish among all those possible models and decide which is the right model. And this takes us all the way back to the basically 17th and 16th centuries with the concept of science. And what is science? Okay. Now in science, we start with a question, and here's a question. Okay, question is, what is the origin of coal? Okay, we got a picture, there's the coal bed, where'd coal come from? Okay, so here's a model. That means there's a possible answer, model A. It's the remains of terrestrial plants. We could come up with lots of models. Coal is the remains of marine organisms. Coal is dinosaur feces. We could go on and on. We could end up with magical products of wizards who have vanished without a trace. I've deliberately chosen this last one as the model Z to make a point. Okay, now our question is, we got all of these possible models, all these possible answers, and what makes one model any better than any other? Okay, now this is the most important idea of all. That is, scientific models make testable predictions. Okay, Novum Organum, Francis Bacon, 1620. Okay, Model A makes a prediction. Okay, this is the model that coal is the remains of terrestrial plants. That is, Model A predicts that somewhere we should be able to find coal, but still with the intact parts of terrestrial plants. That is, leaves, stems, spores, etc. The fact that we find such a thing, and there's an example, piece I took off the AGU website, that strengthens our confidence that actually Model A is the correct model. Okay, and that's why we believe Model A. That's why we believe that coal comes from land plants, because it is so common to find intact parts of plants in coal. Okay? Now, Model C was something about magic and wizards, and they're gone without a trace. I intentionally framed this model so that it actually didn't predict anything that you could go out and look for. Okay, it doesn't mean it's wrong. It's a model, but it's not a scientific model, so it is outside of science. Okay, now we have flooding models, we have stormwater models, and those are representations of reality, and they can be used to answer all kinds of important questions, like how will a change in land use affect the peak flow rate of stormwater? How will a change in land use affect the volume of stormwater runoff? What areas are likely to be flooded due to a rise in sea level or lake level? How could climate change affect the frequency or severity of flooding? Okay. Anyway, all of this sounds great. Okay. We've got models, we've got science, we know we're supposed to test models. So we should have a world where all of our concerns about flooding have been tested and they've been solved. And instead, we find ourselves in a world of many, many bad models. Okay. And the question is, why are there so many bad models? And this is what I'm calling the 9 circles of hell. Okay. Now, so 9 things I want to talk about. I actually came up with a list of 9, and then I realized it was 9 circles of hell. Okay. And these basically go from clueless to criminal. Okay, but not quite that clear cut. Okay. So, number 1, no real modeling is done. Number 2, modeling is carried out by untrained personnel. 3, computer models, that is quantitative, computational models. They're not preceded by conceptual models. 4, the wrong question is answered. 5, model predictions are not tested against observations. 6, model assumptions are not met. 7, models are given inaccurate input data. 8, models are neither verified nor calibrated. And finally, the 9th circle of hell, model input data are deliberately falsified. And there's a special place in hell for people who do that. And I see there's a lot of clergy on the call, so I will let them expound on that further if they care to do so. Okay, so what I'd like to do is kind of give examples of each one of these. Okay, so first is we have models, in quotes, where really no modeling was ever done. Okay, so here's a stormwater pollution prevention plan, okay, from Gulfport, Mississippi. And what do I expect from a stormwater pollution prevention plan? I expect to start off with a description of the current land use, and then what is the current stormwater runoff off of this area? And then there's going to be a change in land use, and I want to expect a model to be run in terms of how is this change in land use projected to change the stormwater runoff. But I don't find anything like that at all whatsoever is being done. Okay, it is simply generic information which could have been cut and pasted from a report on anything. Okay, we should construct silt fences, we should keep the latrines clean, and really there's no model whatsoever, but we do end with a set of conclusions. Okay, now second, I'm still clearly in the clueless area. Modeling is carried out by untrained personnel. Okay, and now what is going on here? The idea is that we have mine tailings mixed with water, And if we let the mine tailings and water sit, the mine tailings are going to compact, so we'll increase their solids content, I guess. The axes titles aren't labeled. Who really knows what's being plotted against what? If you've used Excel, you know that axis title is simply the default. These horizontal lines here, that's also a default. They don't indicate an equilibrium because there's no markers on the right. The idea is that the solids contents are increasing with time, but it looks like somebody shook the whole apparatus about this point, which caused this sudden jump in solids content. We're just told it was done by laboratories in Spain, whatever that means. Okay. Anyway, we're still in the clueless category. Okay, now a little bit more serious. Computer models are not preceded by conceptual models. Okay, so I want to show to you a situation, a conceptual model, and then we'll see what's the model look like that has no conceptual component. Okay, so what happened in Richwood, Texas, following Hurricane Harvey, when all of that floodwater is coming down from Houston back to the Gulf Coast, the city of Lake Jackson builds the Sandbag Dam along Highway FM 2004. So all that floodwater coming from the north, it's ponded behind that dam. Okay, so if we look at the map on the right, we see here's the Sandbag Dam in black, all of those various flooded properties. So after the Sandbag Dam is built, all of these many homes are flooded, some were totally damaged. Okay, so we want to ask, well, what happened here? What's the sequence of events? Okay, so a conceptual model. On the left, you have the LiDAR elevation map, helps to guide creation of our conceptual model. I also visited the site, looked at lots of photos, lots of drone videos. Okay, so that also helped develop the conceptual model. On the right, we have our conceptual model superimposed onto an aerial photo. Okay, so what happened here? We have water coming down the Bastrop Bayou, and it overflowed at this point, and that's when it hit that Sandbag Dam. Okay, so that's why the Sandbag Dam was built, to keep that overflow from Bastrop Bayou from going into Lake Jackson, Texas. Okay, now the water cannot move to the east because it was blocked by this railroad, Union Pacific 66. Okay, so it flows back north. It can't go back into Bastrop Bayou, okay, because Bastrop Bayou was already higher than this floodwater. That's why the water is overflowing out of Bastrop Bayou. Okay, as the floodway finds a path under the railroad bridge, it's flowing along the southern floodplain of the bayou. Okay, now the flood wave can't get back into the river because the river is already at a higher flood stage. Okay, at some point the flood wave finds these drainage ditches and it flows south down the west ditch and east into this east ditch. Okay, from there it flows under the highway into Richwood and also north along East Ditch into Richwood. Okay, it's flowing along the southern path of the bayou. Eventually, it slowly finds its way back into the bayou. Okay, but all of this area and this area here, north and south of the highway, were flooded. Okay, so we see a conceptual model. It's the pathway of the flood wave from the Sandbag Dam through the city of Richwood. Okay, and now we see LJA Engineering, who was hired by the city of Lake Jackson to show that they did nothing wrong. They came to a very different conclusion. Okay, their report has no map, it has no conceptual model, it has lots and lots of tables of computer output. Okay. Now, if we look at this column here, difference in feet, what that's telling us is no difference in water surface elevation between what would have occurred with or without the Sandbag Dam. Okay, so they're saying, yes, Richwood flooded, but it had nothing to do with our Sandbag Dam. And we wonder, how could that be? Okay, because the conceptual model gave such a convincing, I think, explanation as to how the flooding in Richwood occurred. Okay, so what's gone wrong with this model? What's gone wrong with the computer model? Okay, the answer is that the wrong question is being answered. Okay, and this is our point number 4. Okay, it's the right answer to the wrong question. We could say it's the wrong model. Now, if we look at that table on the left, we see that we have water surface elevations, but there's no time. Nothing is saying the water surface elevation on what day or at what time. Okay, so I showed the progression of a flood wave through time and space. So why here do we have water surface elevations with no time component? Okay, now the answer is that what LJ Engineering did is they used a setting on the software that was asking for the steady state solution. Okay, now this is what that means. Okay, so suppose that it started raining hard in the headwaters of Bastard Bayou, and it kept raining and raining and raining indefinitely. So we have a 100-year storm every day indefinitely. Okay, so what would happen? We would develop this wide river that would flow from Bastard Bayou, from the headwaters, to the Gulf Coast. Now, eventually, that river would reach some equilibrium width and depth. Okay, maybe it would take a year, I don't know. And at that point, would it matter that there was a 2-foot-high sandbag dam at the bottom of the river? Well, no. That's why we have all these differences of 0.00 feet with and without the sandbag dam. Okay, so yes, they're right, but they gave the correct answer to the wrong question. Okay, the question was, did this sandbag dam cause flooding in the city of Richwood? And they have answered a completely different question. Okay, so number 5, model predictions are not tested against observations. Now this is very important. So I started from the beginning with what is science, and that is a scientific model, a scientific answer makes predictions that can be tested, which must be tested against observations. Okay, so we have observations. This is the home of Kevin McKinney. He's the director of Richwood Advisory Council, and this is the fence at his house, which I visited, and we see the clear watermark, okay, at this level, okay, which is about 24 inches off of the ground, okay? Now, that model from LJ Engineering, it's making predictions. That's in red if it's a 100-year flood, okay? We see the decrease in water elevation downstream. It's in blue if the 500-year flood. We see a decrease in water elevation downstream. There's a watermark on the highway. There's a watermark on a bridge. And here's the watermark on the McKinney fence. Okay, and we see that that observation does not match the prediction of the computer model. Okay, the computer model predicts that at this fence, the watermark should have been, at least about a foot higher. Okay, so why is that discrepancy? Because the computer model is simply looking at an increase in the water level of Bastard Bayou, which then spreads onto the floodplain. Okay, but the conceptual model says, no, that's not what's happening. You have a flood wave that's approaching the river, Bastard Bayou. It can't get into the river because the river is such a high stage. So actually the water flowing through Richwood is at a lower level than the river, which is exactly what is observed on this fence. Okay, number 6, model assumptions are not met. Okay, we won't worry about the details of the problem here. Just to note that this was work done by Northern Ireland Environment Agency, and they use software. It's software to predict water contamination in a river due to mining discharge. And this is a wild and scenic river, so it's a considerable interest. Okay, we see on the left the software manual, and it states explicitly, Monte Carlo simulation is limited. Requires data are log normal distributed. Okay, nowhere in any document from this environment agency did they ever test the data to show that they're log normal distributed. But I did take their data. Okay, this is stream flow from Corrigan Burn, measured 51,319 times. the probability that those data follow this log normal distribution is 0.000. Okay, so an assumption is required. The assumption is not met. The assumption was never tested by the regulatory agency. Okay, number 7. I see some of you are here from Charleston, so this should be very familiar to you, is that models are given inaccurate input data. Okay, so what we have on the left is a 42-inch stormwater pipe completely sealed with rocks. And we think, well, that's a pretty strange thing to do. There's actually 2 stormwater pipes. On the right is the open pipe, 48-inch open. That's what this pipe on the left would look like if it wasn't covered by rocks. Okay, so the inquiry was made. This was found by a local resident, Jimmy Mazik. Inquiry was made to the city of Charleston, and this was the response. From the records of the work we did to rehabilitate the system in 2015, it looks like the pipe must have been closed off before that. As a result, it would have been done before most of us working in stormwater engineering at the city and county were here. We are looking into if we have any records of what might have happened on the system, or if any of the longer tenured maintenance employees have any knowledge on this, and we will let you know if we find anything out. Okay, so but there was no follow-up on this because the city actually had no record whatsoever of this alteration to the stormwater infrastructure. Okay, now the issue is not just this particular pipe, and it may or might not matter if that pipe is sealed. I actually think it does, okay, but don't need to get into that right now. But the issue is, if you don't know about this alteration in the infrastructure, what are all of the other things that you don't know? And how do you predict anything if you don't even know which stormwater pipes are sealed, which ones are open? Who knows what is even known? Okay, other examples of inaccurate input data. Charleston is kind of a poster child for this idea. These photos are also from Jimmy Mazik, kind of a local hero for his documentation of the stormwater infrastructure. These are the drainage channels. They're nearly full with mud, vegetation, woody debris, trash, sometimes shopping carts. These are not the only photos I have. There's many examples on this, okay? But these drainage channels are used in stormwater models. Okay, those models are used by a consulting company, Seaman Whiteside, to talk about stormwater impacts of developments. I remember earlier, Harriet Festing mentioned that people in Charleston were told, well, if you build developments, it'll actually reduce flooding. Okay, well, that's a result from a model. Where's this model come from? Well, it's based upon this kind of inaccurate input data. But what data was the consulting company using? There was LiDAR elevation data. This is elevation data obtained from aircraft, radar from aircraft. That was collected in 2017. And whatever was the condition of the drainage channels at that moment, that is the official model input, where the drainage channels are now filled with mud, is not taken into account in any modeling. Okay? We're now down to the 8th circle of hell. Somewhat of a continuation of other ideas, but it's important to emphasize, is models are neither verified nor calibrated. Okay, so what do these concepts mean? Okay, verification. Okay, verification means you're verifying the stormwater model is correct, that it is a correct representation of reality. Okay, so how do you verify this? Okay, at one level, we could say, well, you visually inspect it. That often has limitations to what can be accomplished. But in the end, whether you visually inspect or not, you want to assess the functioning of the model as a whole. Okay, so what's done is that a previous storm events are used. Okay, like in Charleston, it could be, say, the April 23rd, 2020 storm event. That's used as an input into a stormwater model, and back predictions are made. Okay, that is predictions of what would have happened in the past. Okay, and those predictions could be certain streets were flooded for certain durations, certain watermarks should be found on certain homes and buildings. Okay, and then these back predictions are then compared with observations. If there's no match whatsoever, we really have to go back to the beginning and reconsider that whole body of input data. But quite commonly, there's some match, but it's not a perfect match. And then we proceed with what is called calibration. Okay, that means that there's going to be certain components of the stormwater model. Well, maybe you couldn't inspect them. Okay, we don't know if they're there. We don't know if they're filled with mud. You make adjustments to those components until you have the best fit between your back predictions and your observations. Okay, and then we say we have a calibrated model, and we're getting a lot more confident that that's the correct model. Now, all of this sounds like a lot of work, but in fact, it's what people do when they actually care about whether the model is correct, as opposed to simply going through a kind of modeling exercise. Okay, and now we're down into the ninth circle of hell. That is the deliberate falsification of model input data. Okay, and this is a little complicated. Let me explain this. Okay, so this is from Houston, Texas, okay? Now, if we go up here, kind of to the north of that picture, is a stream. It's a concrete line ditch, okay? It's called Brickhouse Gully, okay? Now, this area down here near the bottom of the map, it was in the 100-year floodplain of Brickhouse Gully, okay? That is, during a 100-year storm, Brickhouse Gully would overflow, and in a sheet, that water would cover this area to the south, okay? Now, some developers didn't like that because they wanted to build a 900-home development in this area. And they didn't want to do that in the 100-year floodplain because we have restrictions, okay? You can't bring in fill dirt in a 100-year floodplain. You need certain drainage infrastructure, et cetera. That wasn't working for them, okay? They wanted this area to be in the 500-year floodplain, okay? So then they could bring in fill dirt, which they eventually did, et cetera, okay? They'd be exempt from all of those restrictions, okay? So what their consulting engineers did, Jones and Carter, is they said this Brickhouse Gully, and we can see right here, here's Brickhouse Gully coming in from the north and then flowing to the east, okay? This Brickhouse Gully, when it has enough water in it, what it does is it follows this pathway along the dotted line, and then it goes through all those various depressions, and then it rejoins Brickhouse Gully, okay? So that this area is not really in the 100-year floodplain because any overflow from Brickhouse Gully would just be stuck in this drainage channel, and it would not get to the southern area where they want to build 900 homes, okay? Now, one thing I want to point out here, what they call this the split floodway. Okay, so in a flood, 30% of the water, I believe, will go down Brickhouse Gully, and 70% would be in this dotted line, this other half of the split floodway, okay? Now, just to help you understand this, the red colors are high elevations and blue is a low elevation, okay? And this pathway of the split floodway is totally fictitious. How does the water get from Brickhouse Gully into this area of the depressions? It's got to go up and up and up and up, all of these little ridges. It doesn't make any sense. It's certainly on the ground. There's no drainage channel here. Okay, but this is a computer output, so how did they make the computer do that? Okay, now if we look on the right, we have a table of what's called a Manning's N value. It's also called a Manning roughness coefficient. This is a measure of the resistance to flow in a stream channel. Okay, so usually a stream channel might have N equals 0.02, 0.03, 0.04 is pretty high. Okay, so most streams don't have much resistance to flow. Okay, but what they did is they put in a 0.99. Okay, and that would be about 25 times high as, a roughness coefficient would ever get, actually they couldn't put in a higher number because the software they use would only allow 2 digits after the decimal point.
Okay, that's what I need.
Okay?
Can you make a,
So
can you
by
scan
putting
it?
these numbers into the roughness coefficient in Brickhouse Gully, they basically artificially blocked Brickhouse Gully, and they forced the water to jump out of the gully. Okay? So they falsified this split floodway by falsifying input data, and of course there's no confirmation that this split floodway actually exists on the ground, and it doesn't exist on the ground. Okay? Now the scary thing here is that they requested a revision to the FEMA flood zone map, called a LOMAR, letter of map revision, and they were granted that letter of map revision. So the official FEMA flood zone map was revised to suit the needs of developers who didn't want their property to be in the 100-year floodplain. This is pretty frightening because we could say now, how do we ever know when the FEMA flood zone map is based upon science and when it's been revised to suit needs of a developer? Okay, anyway, I already called it the ninth circle of hell, so I don't need to expound on that any further. Okay, now, I've basically talked about what flood scientists can do, which is we can help with all of this unraveling and critique of models. Okay, what can flood affected communities do? I have 3 things in mind. The first is document, the second is document, and the third is document. And I won't bother telling you the 4th thing. Okay, so just going to give a few examples of this. Okay, so this was in the city of Richwood. The owners of those flooded properties, they documented the time that flooding occurred, when they saw water in the street, when water came in the yard, when water came in the home. And then we could make this map of flood arrival times, and we could see that the flooding time is basically consistent with the conceptual model. That is a flood wave coming from the southwest and then spreading to the north and to the south. Okay? And that was very different than what was being proposed by LJ Engineering, which is that there was simply an overflow of Bastard Bayou. Okay, so that was extremely helpful information. Okay, now according to consultants for the city, the floodwater originated in the Brazos River, which they said overflowed, went into Bastard Bayou. Bastard Bayou then overflowed, went into the city of Richwood, had nothing to do with Lake Jackson's Sandbag Dam. Okay, now the many photos and especially drone videos from the residents of Richwood showed that was not correct. Okay, if we look on the left on the Brazos River, it's very famous for how muddy it is. If we look in the center and on the right, we see the very clear water that flooded Richwood. You can see right through the floodwaters, yards, streets, driveways, etc. Okay, very difficult to connect Brazos River with the flooding in Richwood. Okay, more along these lines of document. This is from the City of Charleston, Stormwater Design Standards Manual. This is the key passage from that manual. It's a passage which the City of Charleston actually does not enforce. That is, they do not comply with this manual. But I will read it. Flooding exists in many locations around the city where development densities have increased to the point that stormwater controls have become overwhelmed. The post-development peak discharge rates are restricted to 1/2 the pre-development rates for the 2 and 10-year 24-hour storm event, or, very important, or to the downstream system capacity, whichever is less. Okay? Now, when Harriet was saying earlier that in Charleston, they claim that if you have more development, it'll just reduce flooding. It's because of this clause, okay? They say the post-development peak discharge rate will be less than 1/2 of what it was before the development, okay? But the key thing here is that the real upper bound, the real lower bound on the permissible post-development peak discharge is the downstream system capacity. Okay, so it doesn't matter whether the peak discharge is a half or a third or a tenth of the pre-development discharge. If it exceeds the downstream system capacity, you're still going to have flooding. Okay, and the question is, how do we even know what this downstream system capacity is? Okay, if we don't know which pipes are blocked, we don't know which drainage channels are filled with mud, if we have such poor knowledge of the stormwater infrastructure, how do we even know that? Okay, and this is where the residents of James Island, oh, by the way, this part of James Island is within the city of Charleston. That's why I talk about them together. Okay, so all this information came from the residents of James Island. Okay, that as we looked at the downstream system capacity based upon the actual performance of the stormwater infrastructure. Okay, now I documented 22 flooding events on James Island in 5 years. This came from photos, it came from media articles, it came from social media posts. I probably spent 3 full days scrolling through Facebook, but I eventually did find photos of all of these events. Okay, anyway, I spent a lot of time on Facebook with that. Now, what are we getting out of this? Okay, so let's look on the left, okay? What we're doing is we're looking at which days had flooding, that's in red, and which days did not have flooding, that's in blue, okay? Now, if we have a storm with a return period longer than 4.9 years, the probability of flooding was 100%. That is, it always happened. What if we look at a storm with a return period longer than a year? Now, a 1-year storm is a storm that has a 100% probability of occurring in any given year. So that's the inevitable storm. If you have a 1-year storm, you have a 59% probability of flooding. Now let's look at the diagram on the right. Let's look at days with flooding and days without flooding and compare that to how much rain happened in 24 hours. If we have 5.53 inches of rain in 24 hours, there's a 100% probability of flooding. That is, flooding is inevitable. If we have 2.50 inches of rain in 24 hours, probability of flooding is 50%. That is, flooding is expected. If we have 0.53 inches of rain, half an inch of rain in 24 hours, and that is not at all unusual in Charleston, there's a 10% probability of flooding. Okay? That is, the stormwater system cannot reliably accommodate more than half an inch of rain in 24 hours. Now, that is the real downstream system capacity. So any new development should not have a peak discharge rate that would exceed this very low stormwater flow rate that would correspond to only half an inch of rain in 24 hours. And I would sum that up by saying, you cannot have any new development. You cannot possibly avoid exceeding that actual downstream stormwater capacity. Okay, main thing here, all of this was made possible by documentation from local residents. Actually, the city has no documentation of flooding events. Okay, now there's one idea I want to talk about very briefly without developing the science. It's just something I want you to keep in mind. Okay? In some communities, there might be a controversy about where floodwater comes from. Okay? That was the case in the city of Richwood. Okay? The city of Lake Jackson was saying whatever flooded you, that came from an overflow of the Brazos River that had nothing to do with us. I was saying, and the community was saying that's not true. The flood wave that inundated Richwood, it was the water that was diverted by a dam along the highway built by City of Lake Jackson, in case there was a controversy. Sometimes there might not be no controversy, okay? No one's disagreeing about where the flood water is coming from, okay? But suppose there is, okay? This would be the frontier of community documentation of flooding. I don't think this has ever been done in terms of resolving a dispute about where flooding came from, okay, even though it's been done in many other scientific contexts, okay? So the idea is that a community would need to collect flood samples in airtight containers. So they would need to have the containers in advance of the flooding event. They would need to anticipate that this would happen, okay? Now, what can be done next is you measure stable isotopes in the water, okay, that is stable isotopes of hydrogen and stable isotopes of oxygen. Now, that isotopic signature depends upon the whole history of that water. Its evaporation, its condensation, its precipitation, etc. Okay, and if we see on the left, we have that green line and blue line, they're almost in the same place. Okay, that's the isotopic signature of precipitation. Okay, so any water samples from anywhere that fall along this line, we would say, oh, that's just rainwater. We know where that's from. Okay, but now we have this other red line called the evaporation line. Okay, now this is water that fell as rainwater, but then it sat and evaporated for some period of time. Okay, now in this community, this is in Brazil, there were villages that were just downstream from a very large mine tailings pond, the largest gold mine in Brazil. Okay, the tailings pond held 400 million cubic meters. Okay, it's not a small pond. Okay. Now, the question is that tailings pond water getting into people's water supply? Okay, well, we see that some of those water samples had the isotopic signature of water that looked like it had been in a pond for a long time, and it happens that two of those points are the drainage pipes that come out of that pond. Okay, now if we look on the right, there's a hand-dug well in the village of Santa Rita. It's not Santa Rita because it's Portuguese, okay? And that has the isotopic signature of the upstream mine tailings pond. Okay, so this elderly gentleman, we believe, was in his water supply, he was getting water seeping out of the mine tailings pond. Okay, I'm not developing the science of this any longer. It's just something I would like communities to keep in mind of this possibility. And with that, I'm happy to take any questions.
Do you want to stop sharing? I think that might be the easiest way to do it.
Indeed, I stop sharing.
Yay, wonderful. Thank you. Thank you. Thank you so much. So helpful.